Hi everyone. Have you ever been in a pickle that your queries are running slow and you're trying to figure out how to lay out your data? If so, you're at the right place today. In this talk, we'll cover liquid clustering, our innovative data layout technique on Delta Lake. We'll first touch on the benefits of liquid clustering and its reception from customers, followed by a technical deep dive into how liquid clustering works under the hood. Last but not least, you'll hear from us in terms of some of the best practices of using liquid clustering. So before we get started, just a little bit about myself. I'm Cindy. I'm a product manager here at Databricks working on the Open Lakehouse, as well as how we can bring data intelligence to your tables. And I have Rahul here with me. He is the technical lead of liquid clustering and one of the smart brains behind all the awesome improvements that you're about to hear. OK, so why are we here today to learn more about data layout? We all want our queries to go fast. And one key factor here is indeed the data itself. Applying the best data layout to your tables can improve query performance and cost efficiency by a lot. However, it turns out that choosing the best data layout is actually a really hard problem. So before I get into the details for liquid clustering, let me give you a background of why we work on liquid clustering in the first place. As you may know, there are the existing techniques for optimizing your data layout, such as partitioning and z-ordering. They're good for performance, but tuning them to get to the optimal performance is not straightforward at all. The feedback we heard from customers is that it's actually very difficult to design the right partitioning strategy to avoid data skews and concurrency conflict. Think about the most recent time you were setting up a new table with new workloads. If so, some of these questions might came to mind. For example, you may be mixing partitioning and z-order, so you have to make decisions about which column to go to partitioning and which columns to go to z-order. Also, you have to be careful about the cardinality of a column when choosing partitioning columns, because choosing a high cardinality column will not scale due to the small file problem. Last, if query patterns actually change and you want to change your partitioning columns, you have to rewrite the entire table, which is not flexible at all. And on top of everything, z-order is super expensive to use and even more complicated to manage. So to solve all the problems I described so far, here we comes in liquid clustering. It is fast. In fact, the right performance could be faster than partitioning in z-order. I'll share some results in a bit. It also has very similar read performance out of the box, even compared to a very well-tuned partition and z-order table. It is also incremental, meaning that it only clusters the data that needs to be clustered, which leads to lower write amplification and fast clustering time. It is also self-tuning and skew resistant. So what does that mean? With skews, you could get slower queries from a partition that just happen to have a lot of data. In contrast, with liquid clustering, you don't have to worry about the cardinality of a column when choosing a clustering column. This was not the case when picking for partitioning. And last but not least, it's super flexible. You can change the clustering columns at any time based on your needs without having to rewrite the entire table. And what is the net effect of all these improvements? Liquid clustering is far easier to use than partitioning. And on top of that, it brings you blazingly fast query performance, even at the petabyte-scale dataset level. So first, let me share a bit about why liquid is far easier to use than partitioning. So I said it was super simple. How exactly can I use it? Well, you just need to use the cluster by syntax when creating a table. And Delta Lake liquid clustering can handle everything else for you. You don't have to think about your data characteristics, such as cardinality or skew. And if you want to change the clustering columns, you can simply use alter table cluster by and specify the new columns. And in addition to that, you can use the same alter table syntax to migrate from any existing unpartitioned tables to liquid in place, meaning that you don't have to rewrite your unpartitioned tables. And how does this compare to partitioning? Partitioning is very static, as it cannot be adjusted after a table creation. If you want to change your partitioning strategy, the entire table needs to be recreated. And in contrast, liquid clustering is very flexible. You can change the clustering keys as your business needs evolve and recluster the table as needed. And moreover, with liquid clustering enabled, it actually lets the Databricks Data Intelligence platform to automatically handle and resolve concurrent transactions for you. So let's consider this example. You have two writers from two different sources. Let's say you have some sales data coming in from different countries, some from the US and some from the UK. And you're attempting to write at the same time, merging into a global sales number table. And this table is partitioned by date, which is a very common partitioning pattern we see from customers managing large data sets. So suppose the sales from the US are written to the table with the stream A, and the sales from the UK is written with stream B, you see on the slides. So here, if the first stream stages its commit first, and the second stream tries to modify the same partition, Delta Lake would actually reject the second write at commit time with a concurrent modification exception, even when the two writers are actually modifying different rows. This is because with partition tables, conflicts are detected at the granularity of partitions. As a result, the writes from the second stream are lost, and a lot of compute can be wasted. So to handle these conflicts, you can redesign your workload with retry loops, which will attend the second stream again. However, the retry logic can lead to increased job duration time and compute costs by repeatedly trying the same write again and again until the commit is successful. So finding the right balance is really tricky. Too few retries can risk failures, while too many might cause inefficiency of very high cost. So another approach here is to do more fine-grained partitioning. But managing a more fine-grained table partition to isolate write is also very difficult. Especially you have multiple writers writing to the same table. So in this example, you actually could rewrite this table and partition by date and country. But then this would cause the small file issues. This would happen when some countries get more sales data, while other countries get less sales data. And this is, again, a very common data pattern we see. But with liquid clustering, it actually avoids all these small file issues. But together with our Databricks Data Intelligence platform, we actually provide row-level concurrency and gives you concurrency guarantees on the row level, which is more granular than the partitioning level. If you're curious about how this is done, you'll very soon hear from Rahul on how row-level concurrency works behind the scenes for Liquid. So to quickly summarize, with liquid clustering, you no longer have to worry about cardinality, key order, table size, data skew, concurrent transactions, or how access patterns might change in the future when choosing your data layout. And this is what makes liquid clustering a lot easier to use than partitioning. And on top of the simplicity aspect, we have also seen that liquid clustering can really speed up your query performance. So we measure the performance of writes, which includes ingestion time and clustering time, using a 1 terabyte industry standard benchmark data set. So in this setup, we are also clustering frequently to make sure that the clustering quality is high. And liquid clustering was 7 times faster than the partition and z-ordered table. We also have a result for read performance. So this result is actually from a large manufacturing company who is a customer of ours, and they saw up to 12 times faster read performance after migrating from a partition table to liquid tables. And moreover, one of our top 5 Databricks customers actually did an extensive benchmark on liquid clustering compared to partitioning on representative workloads. And their POC results showed that liquid clustering is overall 4 times faster than partition tables across the test queries. They also specifically tested for the scenario where partition can produce a lot of small files. And in those test cases, liquid is actually 45 times faster across all queries. And with all this awesome improvement, let's see how our adoption looks like. We're overwhelmed by our customer adoption. Liquid clustering has been one of the fastest adopted capabilities at Databricks. We have more than 3,700 active weekly users, and this number has been growing every week. The largest table we have in production is more than 10 petabytes used by customers, and we have many tables in the 100 terabytes range, and it shows that liquid clustering can truly scale. Does anyone know roughly how 1 petabyte is? This is an enormous amount of data. To put it into perspective, this is roughly equivalent to every book ever written, roughly 20 million books. Also, we have more than almost 2 exabyte data written to liquid tables and over 200 exabyte reads from liquid tables since we have G8. But liquid is not about how much data we read. It's actually about how much data we skipped. So a quick pause here. Can you guess how many bytes of table liquid clustering actually helps us to skip? And the answer is 9 zettabytes. And in case you're not familiar with zettabytes, 1 zettabyte is equal to 1,000 exabytes. This is a huge number. So if 1 gigabyte is like a book, then 1 zettabyte is like every book ever written multiplied by 1 billion. And that's exactly what we wanted to see with liquid clustering, which helps our customers skip as many data as possible when querying their tables. We also had great endorsement on liquid clustering from our customers, like Shell, Ipidata, and Cisco. The feedback has a common theme. They all like the query performance improvement. So just to quote some of the quotes here, liquid clustering improved our time series queries up to 10 times, and we have observed remarkable improvements in query performance compared to the traditional Z order, and so on. Also, they mentioned the ease of use, such as without worrying about the cardinality or file sizes, eliminating the partitioning bottlenecks, and reducing the data skews. It was very humbling to hear such great feedback, because this feedback matched exactly our goals for liquid clustering, providing really fast performance and ease of use at the same time for our customers. So if you haven't tried out liquid clustering, please go ahead and try it out today and give us any feedback you might have. So with all these benefits in mind, you might wonder, how does liquid actually work under the hood and achieve all this incredible performance? Let me pass it on to Rahul to tell us more about how liquid actually works under the hood.
Thank you, Cindy. Now I'll be doing a technical deep dive on liquid. But first, let's try to answer the question on what makes an ideal data layout. There's in fact 2 important things. The first one being file sizes. So file sizes determine how many files you have in the table for the same amount of data. So let's say you have small files, like around 1 megabyte and lower. In this case, you end up doing more cloud requests to serve the same amount of data. And you incur an additional cost just to open these files on the cloud. And finally, there's a good chance that you might run into metadata bloat issues, which cause scalability and performance problems. On the other end of the spectrum, you could have large files, greater than 2 gigabytes each. Here, it becomes really hard to parallelize the queries to run across multiple CPUs. And at the time of writing, you also incur the additional cost of writing it serially, so it's going to be slower. And compared to the smaller file sizes, it's going to be worse for selective queries as well. So at Databricks, we have identified 16 megabytes to 1 gigabyte as the ideal file size zone that you want to have your tables in. And this is through years of benchmarks, working with our customers, and some research that we figured this out. And at this file size range, we know that the metadata is constrained. It's better for selective queries, and you get better parallelism. I like to make the solar system analogy here. Like file sizes between 16 MB to 1 gigabyte is similar to how the Earth is in fact at the perfect distance from the sun, not too close like Mercury, not too far like Jupiter, where you have a thriving civilization. With that said, the second important point about data layouts I wanted to talk about is the data range. This example here will illustrate what data ranges are and what we want them to be. So in this query, I want to get all the records for the date Jan 3rd. If I had a layout like the one on the screen, where I had 5 different files, and all 5 of them are overlapping, what happens with a query like this? You basically end up reading all the 5 files. So you can imagine at scale, if you have 1 million files and you have select a query with an overlapping range, you might end up scanning almost 1 million files to serve a simple query like this. So that's why we recommend having non-overlapping data ranges. And what that means is Each file has its own distinct boundary of data, what it contains. And the same query here has to read just a single file. So it's much more efficient, right? So to summarize what an ideal data layout is, basically, you want file sizes between 16 MB to 1 GB, and you want non-overlapping data ranges. And more importantly, you also want the cost of maintaining this layout to be bounded. What that means is lower write amplification, and your maintenance operations like optimize have to be incremental and only rewrite the new data and not the existing data. Now, let's apply this framework with partitioning and see what the problems are. So for this example, I've taken a table that's partitioned by date and customer ID. Many of you might have similar tables in your fleet as well. And I'm going to ingest data hourly in an incremental fashion. So after a day's worth of ingestion, what I see here is there's pretty good data range because all the data is non-overlapping on the partition column, the customer ID. And if you repeat this for one more day, you also see that even with respect to date, you have non-overlapping data ranges. But after ingesting for 3 days, you may start observing a pattern where some of your customers are like whales, where there's a lot of files in their partitions. And some customers are minnows, where there's only one file or no file in some of their partitions. Another thing you'll observe as you start using this table is the queries are going to be slower. This is because we have too many small files in the table. So you end up, for the reasons I mentioned before, the queries are going to be slower. So what do? You say run optimize to compact these files. While that's the right thing to do, you do end up with a problem where optimize is only able to compact within a partition boundary. So what that means here is only the whale customers end up with like good file sizes, whereas the minnow customers like customer D, E, and F had only one file to begin with, so compaction really can't do any better. So this problem still persists, so you end up with slower reads. What is the solution here? You may say, hey, why don't I partition by week? There's actually two problems there. One, you need to rewrite the whole table to change the partitioning key. There's no way to update the partitioning. And there are customers like the whale one here who actually do good with the date partition. So we could actually make queries on the whale customers worse. So to summarize, what are the challenges we saw here with partitioning? We saw small files, data skew, and slower writes as well when you're actually writing this out. And last but not the least, it's static, meaning if you make a mistake in choosing the layout, you have to rewrite your whole table. We have another technology called Z-ordering, which solves some of the problems with partitioning, but the challenges here are it's not incremental, and you need to really tune these workloads via maintenance operations to get like good performance. And with maintenance operations here, there's a risk of conflict with existing business transactions that might cause even more delays. Now, finally, let's get to liquid clustering. Let's try to apply the same example into liquid clustering. So let's see how to create the table first. So very simple. You take the same data. Instead of doing partition by date and customer ID, I'm going to be doing cluster by date and customer ID. So let's say you end up with the same ingestion. Now, when you want to like run optimize to compact the data, liquid clustering is actually very intelligent because it works backwards from the target file size. It knows what the target file size is, and based on that, it goes and figures out what the clustering data ranges should be. So because of that, you're now able to see good file sizes within the range that we described previously, and really good data ranges that give good clustering performance as well. So this framework we defined is satisfied for liquid clustering, right? Well, you may say, yeah, that was easy. That was just a one-time thing. What happens if you have more data coming in? Because your applications don't just stop, right? You are always producing more data. It's actually, it works the same way. So if you had new data coming in, let's say into the June 13th area, so now liquid clustering is actually smart enough to know that the old data is already well clustered, so I don't have to go and rewrite the old data. So even within the new data, we have a cost benefit model where we can see that the red box in this image in customer CB and A bucket does not need to be rewritten because it's already a single file. You can't really improve anything there. Whereas the red box in the bottom part of the screen is actually small files which can be rewritten to get better file sizes. So we end up rewriting them. So by choosing less data to rewrite, we're actually making things efficient and faster in terms of maintaining the table. So far we covered just the basics of liquid clustering. Let's see how liquid clustering does on the Databricks data intelligence platform. So on the Databricks platform, we have more information about workload and patterns. So we're able to have more features like clustering on write, which allow you to cluster data as and when you ingest without waiting for maintenance operations. So let's say this data that I'm ingesting does not only contain data for the 13th of June, but also 11th and 12th. Again, many of you might have seen this pattern before because backfills are pretty common. Late arriving data is pretty common. So what happens here is we're able to remap the ingested data while it's ingesting into the layout of the underlying table. So we're able to know what the layout looks like and what the ingested data needs to look like. And basically what happens is we can go and co-locate the new data into the same layout as what we had before. So what this gives us is no write amplification. You didn't have to run optimize to do table maintenance. And you get the improvements immediately. You don't have to wait for your maintenance operations. OK, so appends are easy, right? Let's talk about deletes. So previously, let's say you had a file like this, and you just wanted to delete a single row, let's say row 0. Previously, what would happen is to delete a single row, you have to go read the file, remove that row, and write that file back again. So this is what we called as copy on write. With liquid clustering, all tables that have liquid clustering enabled come pre-enabled with deletion vectors. So the same delete now is much more efficient because we don't have to go and read and write the data again for that file. We just have to mark the deletion vector for those given rows that we deleted as true, as you see in this example here. So when you have hundreds of columns or maybe even thousands of columns, this can be really helpful in reducing amount of data to read and write. So we spoke about ingestion so far, but as you know, applications get more complex. You may have started with just a single producer of data, but as your application evolves, you might have multiple producers, and you might be wondering, hey, how do I deal with concurrency? So with partitioning, concurrency is based on the partition boundaries. So let's see how that works. So if I have merge 1 that's operating on partition for date June 11th and June 12th, and I have another merge 2 that's operating on partition for June 10th. Actually, this works perfectly. You don't need to do any sort of orchestration. This just, no conflicts. It just goes ahead successfully. Let's say, incidentally, merge 2 operated on June 11th, same as merge 1. In this case, with partitioning, you actually see a conflict, and you have to rerun and reorchestrate the failed transaction to make sure that there's nothing else operating on the same partitioning at that time. So this is the thing we wanted to solve with liquid clustering, where we didn't want you to think about what your partitioning is, what your data layout is. We just want you to concentrate on the application. And with liquid, let's say you have 2 merges operating on the same dates. You may also have optimize operating on the same date. Let's say you also have some GDPR update deletes operating at the same time. all of this will succeed without conflicting, even if they're on the same file or partition level. Because with Liquid, the conflicts are, you no longer conflict as long as you're writing and updating different rows. So you don't have to think about reorchestrating your jobs with like failures and try catches and whatnot. So let's see how this actually works. So let's say I have file A with a deletion vector in table T. Now let's say I have transaction A that's going and deleting row 1. And at the same time, there's another transaction B that's going and deleting row 3. Because let's say A started first, so A might commit first. So the first transaction that commits never has any issues, right? But transaction B, previously, without row-level concurrency, it would have failed, making you to retry. But with row-level concurrency, we're able to actually rebase transaction B on top of the committed transaction A. And how that works is you take the deletion vector for transaction B, you also take the deletion vector for transaction A, you combine them, and you write out a single deletion vector that reflects both transaction A and transaction B, and then you commit. So no conflicts anymore. Right, so all this time we've been talking about ingesting more data. Well, if you ingest data and don't use it, it's pointless, right? So let's now talk about how query performance is in liquid clustering. So you might, after ingesting a lot of data, you might run a query similar to this, where, hey, like how many records did I ingest for every date? And this is a type of query which is actually super fast on liquid clustering, because with data intelligence, we're able to figure out file-level partial aggregates from just the metadata. This allows us to like skip reading files altogether. And this can be up to 20 times faster, according to our benchmarks. And how this basically works is, let's take the same table we had previously. One thing you observe here is there are some files where the entire files contains a single day, right? So like, for example, the June 11th file, all the files in the June 11th file will be June 11th, right? So the partial aggregate for that file can be simplified as the row count. And row count is something that's already available in the metadata. So we can get the partial aggregates without even reading these files. And for the two files that have a more wider range, you can actually aggregate them by reading those files. And finally, you combine both of them together, and you have your answer, except it's going to be so much more faster because you only read 2 files instead of 10. So with this, you can have like super fast aggregation queries by avoiding files to read altogether. Similarly, we've improved join performance as well with liquid clustering. And this is a common pattern where you have a fact table that's very large, and you have a dimension table that's smaller, and you might have a filter on the dimension table, but not on the fact table. So what we do here is we have a technique called dynamic file pruning, where we're able to figure out what files don't match the condition of the dimension table on the fact table side, and we're able to reduce the files to read for the query. With this, you're able to see like up to 10 times faster join performance and even merge performance, because merge also has joins under the hood. And this is currently supported for all types of joins, including shuffle joins on Databricks. And you may ask, like, hey, we ingested all this data, we're running these queries, how well does it scale? All these optimizations are supported at the petabyte scale, and as Cindy was mentioning, our largest table in the fleet is upwards of 10 petabytes. Let's actually look at some fleet numbers to see how well we have done. So we announced liquid clustering in 2023, 2 years back, and these are like the fleet P95 numbers of like clustering on write from that year compared to this year. And we have improved our engine to be 8 times faster than what we started off with. And these are, in fact, for ingestions greater than 10 terabytes. And similarly, for Optimize that runs on tables greater than 100 terabytes, we've improved our performance more than 20 times since we first announced liquid clustering 2 years back. And there's a bunch of new features we are releasing as well. So today I'm excited to announce selective override capability for liquid clustering. So you may have tables that you want to update selectively, where based on a predicate, you want to replace all the rows that match that predicate on the table with new data. And with the help of this new syntax called replace using, you can do it as a single atomic command. With that, I'll hand it back to Cindy for some best practices.
Thank you, Rahul, for the deep dive. And I hope that was helpful for you to learn why liquid clustering is so powerful, even on such a massive scale. So now with all these latest improvements, what are some of the best practices to use liquid clustering? So one thing we get asked a lot is, how frequently should I run Optimize? So the rule of thumb here is you should run Optimize when you have new data arrived. And Optimize can incrementally cluster your data for the best clustering quality. And if clustering on write is enabled, we still recommend you to run Optimize. This is because clustering on write clusters only the newly ingested data. In contrast, Optimize can look at your entire table and determine the globally optimal clustering data layout. And again, it incrementally adjusts the existing data layout to match the global optimal. So another question we get asked a lot is how to choose the best liquid clustering keys. So we recommend choosing the keys purely based on your query patterns. So you don't have to worry about things like cardinality, key order, table size, data skew, or how your data would evolve. By the way, actually the last time I have to set up a liquid table and pick the right clustering columns, it actually took me a long time to figure out what my query patterns are, because they just don't exist yet. And this is why we built automatic liquid clustering to solve this problem on UC managed tables. So with predictive optimization, we completely make data management hands-free for you. It also helps you apply liquid clustering on the long tail of tables that you simply don't have the bandwidth to manage. So now before I dive into automatic liquid clustering, let's do a quick recap of predictive optimization. So you might actually have heard about this from Mahadev this morning in the keynotes. This is one of our most important features that brings data intelligence to your table to provide the best price performance. It is also a prerequisite for automatic liquid clustering. So predictive optimization can capture your data and query patterns through the Unity catalog on your UC managed tables to determine the best optimizations to run on your data, and actually runs those optimizations automatically on behalf. And this is because we have all the reads and writes access captured through the Unity catalog, and we can understand exactly how your table is used and its characteristics. So currently, with predictive optimization in general availability across all the 3 clouds, we support Optimize, which improves your query performance. We support Vacuum, which improves cost efficiency by deleting unneeded files. We also support Analyze, which update the stats used to optimize query plans. By the way, remember earlier I also mentioned that you should run Optimize, which incrementally clusters the data coming to your liquid table. So predictive optimization actually does this automatically for you. It can detect that when new data has arrived, which results in unclustered bytes in your table, and it would run Optimize on your behalf at the best cadence. So now let's see how AutoLiquid works in action. So by simply running create table or alter table cluster by auto on your UC managed tables, predictive optimization can come in and choose the liquid clusterings on your behalf. So how does this work behind the scenes? So first, we would collect the query scan statistics, such as query predicates and join filters, to determine if the table would benefit from adding or evolving liquid clustering keys. And then we'll actually choose some candidates by looking at your query workload, and we would tell what are the best columns to provide the maximum amount of data skipping if we set them as clustering keys. So here we can actually adaptively learn from your table's workload history and calculate the potential savings of having some clustering schemes based on how much data skipping they can provide. And for each of the possible clustering configuration, we will actually simulate past queries to predict how much data skipping can perform. And finally, we want to make sure that any changes to your clustering keys actually provide a meaningful performance gains, as clustering can introduce additional overhead. So once the best clustering key candidates are identified, we actually evaluate whether the benefit of applying or evolving the clustering keys would outweigh the cost itself. And if the benefits are clear, we'll actually proceed with updating the clustering keys on your UC managed tables. So the capability in a nutshell, we would choose the liquid clustering keys on your behalf such that the predicted cost savings from data skipping would outweigh the cost of clustering. And what is the net effect? You can really just enjoy automated clustering key selection with AutoLiquid. The data writing to your table will also be automatically clustered. You can just sit back and enjoy faster queries and a lower total cost of ownership without a lift of a finger. And now let's look at how customers have reacted to this feature. So customers such as Branching Minds has closely monitored their queries performance and actually saw a lot of improvement. For one instance, their average query times actually went from 100 seconds to less than 1 second. And we also hear from other customers that their queries actually ran up to 10 times faster with automatic liquid clustering. And in addition to the performance improvement, we hear from customers that they really love that the heavy lifting of tuning and maintaining the layout is actually now done by AutoLiquid automatically. It saves a lot of valuable time for them because they no longer have to do the manual work of tuning the tables themselves. So other customers also see how this actually completely eliminated any manual data layout work needed for them. And lastly, we're super excited to see that customers actually broadly adopting AutoLiquid tables. Some of them enabled on thousands of tables in production environments. It's also really easy for them to see that their compute cost actually has gone down over time. So just to quickly summarize, as our best practice, we recommend using liquid clustering on managed tables with predictive optimization so that you can have the best data layout out of the box with maintenance operations run at the best cadence for the best query performance and storage cost efficiencies. So with that, the key takeaway for today is that with liquid clustering, it's super easy to use. You can be hands-off, and liquid is actually highly flexible. Liquid clustering can improve your query performance by a lot, and is also super efficient, even at the petabyte scale level. So I know this is the last day of Summit, and some of you might be ready to go to happy hours or go home. So if you walk away with only one thing from this talk, is that liquid clustering should be your only data layout of choice. Thank you.